Hi, calculus students. These notes are on related rates problems, and so I'm kind of outlining at the top for you a series of steps that we can follow. So what I'm going to do is kind of go step by step here and show you what that looks like with this example problem below. So the first step is to assign letters to all quantities that vary with time. That's kind of a key piece of this. And any others that seem relevant to the problem, give a definition for each letter. And I'm also going to say we want to include units here, because units are going to end up being very important, and they're also going to help you know like what quantities you're given versus what you need to find. So that's something we just want to always keep in mind. So if we read this example, he says, assume that oil has spilled from a ruptured tanker in a circular pattern, that's going to be important, whose radius increases at a constant rate of 5 feet per second. How fast is the area of the spill increasing when the radius of the spill is 25 feet? Okay, so if I'm thinking about what my variables should be, well, there's two key quantities that I see here. And the key for when we think about the variables, I want them to represent amounts of things, not rates of change. So that would be radius and area in this problem. So I could say R is going to be the radius of the spill. And A is going to be the area of the spill. And I might just kind of put it to circle, just to kind of help me when it comes time to write an equation. Now, what are my units? Well, at one point I know that the radius of the spill is 25 feet, so then that I assume that radius should be in feet. And for area, well, if my radius is in feet, my area should be in feet squared. So I've done with step 1. Step 2 says, identify the rates of change that are known and the rates of change that is to be found. Interpret the rate as a derivative. So the idea of interpreting the rate as a derivative is to do like d something dt, right? So we think about what is known and what is unknown. Well, what is known is that the radius increases at a constant rate of 5 feet per second, right? So if the radius is increasing at a constant rate of 5 feet per second, that would be the derivative of the radius, or the rate of change of the radius. So let's call it dr dt. And we know that is 5 feet per second. Okay? What is unknown? Well, that's kind of getting at what are you being asked to find. So the question that's being asked is how fast is the area of the spill increasing when the radius of the spill is 25? So let's call the unknown then the rate of change of the area, so it would be dA dt. And we're specifically like to know what this is when the radius equals 25. Right? And that's just kind of useful to keep in mind. Eventually, there's going to be a moment where we get to plug that in. But the key is we don't want to plug it in before we take the derivative of the function that's relating the two quantities. So what are my units for the rate of change of the area? It should be the units for area, feet squared, per the units of time. And I know my units of time if I'm looking at this rate, so I know I'm in seconds. So it should be feet squared per second. Okay, so now let's see. The step 3 then, let me go scroll back up here. Step 3 says find an equation that relates the variables whose rates of change were identified in step 2. To do this, it will often help to draw an appropriately labeled figure to illustrate the relationship. Okay, so the idea here is, well, we have some oil spill, and we know it's a circle. So our diagram is pretty simple. It's just going to be a circle, and we can label the radius r. And then we also know that the area of this thing should be the area of the circle. So that helps us kind of set up our equation. We can say area equals, what's the area of a circle? Pi times the radius squared. Okay, so that's all I really need to do for step 3. And notice that I just wrote an equation that involves both the r and the a from step 1. So now, for step 4, it says differentiate both sides of the equation it obtained in step 3 with respect to time. So the idea of doing it with respect to time means you need implicit differentiation. To produce a relationship between the known rates of change and the unknown rate of change. Okay, so I'm going to scroll down. So I'm taking the equation a equals pi r squared, and I'm taking the derivative of the whole thing with respect to t. There are no t's in this equation. So what that means is both a and r are some other functions of t that I don't know, but that means I have to do the chain rule when I think about taking their derivative. So the derivative of a, well, if a was just a regular t, its derivative would be 1. So that means that the derivative of a is just 1 times the derivative of a, dA dt, is equal to, so the idea on this side is I need to do the chain rule where r is some inside function. So it would be, how would I take the derivative as if r was a t? Well, I'd bring down the 2, so it'd be pi times 2r. But then r is another function, so I have to do the chain rule and say times dr dt. And then I could just kind of make this look a little bit nicer by putting the 2 in front of the pi. So this is really 2 pi r dr dt is equal to dA dt. Okay. At this point, something really nice happens. Right now, it looks like I have 3 kind of unknowns in this equation. I have dA dt, I have r, and I have dr dt. But if we kind of read through what step 5 is, it says after completing step 4, substitute all the known values for the rates of change and the variables, and then solve for the unknown rate of change. So even though we had 3 variables at this point, we actually know what 2 of them are. So I know that I'm trying to find dA dt, right? If we go back to step 2, that's my unknown. But I do know that I'm interested in it when r equals 25. And I also know that the rate of change of the radius is 5 feet per second. So I can plug in 5 for dr dt and 25 for r into my derivative equation. And then I should be able to just get a value for dA dt. So I substituted those known quantities in. Now everything on the right-hand side is a number. I can type this into my calculator, and I'm going to get an approximate answer here. So when I punch this into my calculator, I get 785.4 about. And then I don't want to forget what my units are, so it's feet squared per second. If I didn't remember, that's where you could kind of refer back to the earlier step where you decided what units am I going to use for the rate of change of the area. The last thing I want to say is it's a good idea to then, don't just write your number, actually say, what does this number mean? So it means when the radius of the spill is 25 feet, the area is increasing at a rate of 785.4 feet squared per second. Okay, and if you think about it, like that seems like a really big rate of change. But if you think about what a 25-foot circle it looks like, that's a pretty big circle. So at that moment when the radius is that big, as the radius starts increasing even more, the area is going to balloon at a much faster rate. Okay, so to finish up for homework, what I'd like you to do is see what you can do with the problem on the back. So there's another problem that is similar to this one. I think it's a little bit simpler even. So see how far can you get with example 2 in going through the steps. And we will talk about this in class.